Hello everyone, and welcome to another lecture related to the physical pharmacy module. So this lecture is supposed to be given today, the 14th of March 2020. The time of the lecture is supposed to be 9:30 to 10:20 a.m. according to the weekly timetable. In the last lecture, we already covered all these topics. So after the identification of and description of the four colligative properties of non-electrolyte solutions and understanding the various types of pharmaceutical solutions, and then after the calculation of the concentration, the different concentration expressions such as molarity, molality, normality, mole fraction, and so on, and also the equivalent weights, and also the discussion related to the ideal and real solutions using Raoult's and Henry's laws, and also the final thing was how to use Raoult's law to calculate partial and total vapor pressures. So today we are going to move to the next and the last section of this chapter, which is related to the calculation of the four colligative properties related to the vapor pressure lowering, boiling point elevation, freezing point lowering, and the pressure of solutions of non-electrolytes. And the other thing is how to use the colligative properties to determine the molecular weight. So yeah, these are the topics for today's lecture. Just to remind you very quickly that what we mean by the colligative properties, such as the freezing point, boiling point, the osmotic pressure, and the vapor pressure of non-electrolyte solutions, these properties are depending on the relative proportion of the molecules of the solute and the solvent. So that's what we mentioned before, and the name, the colligative properties, came from the Greek word. It means collected together. So because these properties are dependent on the number rather than the nature of the constituents, as we mentioned before. Now this slide is showing how to calculate the first colligative property, which is the vapor pressure lowering of non-electrolyte solution. Now imagine, before going into the details of the calculations, I just wanted to give you some information why the vapor pressure lowering is important for us. So imagine that we are making a solution, a pharmaceutical solution. So in order to do that, we need to dissolve a solute in a certain volume of the solvent. What they notice that when you add the solute, there will be a change in the vapor pressure of the solution compared to the vapor pressure of the solvent. Okay, and that's why this is happening, and why this is important, because we notice that there is a change in the vapor pressure of the solution compared to the original vapor pressure of the solvent, and that's what we call it the delta P. Okay. So in order to see how this is happening and how to calculate the amount of the solute that caused this lowering in vapor pressure, we need to go to the details of this lowering. So what they notice that this change in vapor pressure lowering is depending on what? On the concentration of the solute in the solvent, on the number of moles of the solute in the solution, okay, or the number of moles of the solute in the solution. Okay, so in this case, that's why we call the lowering in vapor pressure as a colligative property. Why? Because it's actually depending on the number of molecules of the solute in the solution, as it can be seen in this equation. So in this equation, the delta P over P1, what we call it the relative lowering in vapor pressure, is equal to the mole fraction of the solute, right? So that's equaling to the number of moles of the solute, which is N2 divided by N1 plus N2, which is the total number of moles of the solute and the solvent. So this is very easy, can be calculated in the equation. So if we know, for example, the molecular weight and the weight of the solute and the solvent, we can easily calculate the lowering in relative lowering in vapor pressure. And also, if we know exactly the vapor pressure of pure solvent, we can calculate the delta P, which is only the lowering in vapor pressure between the pure solvent and the solution. So that's the way on how to calculate the lowering in vapor pressure of non-electrolyte solution. And this example 5.8, show you a very simple example, which is the solution of saccharose in water, and how can you calculate the relative lowering in vapor pressure of this solution. And if you want to know more information on how to get this equation, or more examples on how to calculate the vapor pressure lowering of another kind of solutions for non-electrolyte, you can get this information in pages 227 to 228 in Martin's Physical Pharmacy book. The second important property related to the solutions of non-electrolytes is the elevation of boiling point. So what does it mean? What they found that when you make a solution, imagine that you are making a pharmaceutical solution. So they noticed that when you put the solute in the solvent, the boiling point of the solution will be higher compared to the boiling point of the solvent. And as you can see in this figure, the first figure, as the concentration, for example, of saccharose expressed as a molality of saccharose increase, the boiling point is increasing. So what does that mean? What does it mean? That the boiling point of the solution is depending on the concentration of the solute in the solution, and that's why the elevation in the boiling point is considered as a colligative property. Now, another important question is this: why the boiling point of solution is higher than that of the pure solvent? The reason for the elevation of the boiling point is because the solute molecule try to decrease the vapor pressure of the solution, and in this case you need more heat to reach the point of the boiling of the solution. So and there is a relationship between the pressure, the delta P, which is the one between the pressure of the solute and the solvent, the pressure difference between the solvent and the solution, and also this cause elevation in the temperature required to reach the boiling point of the solution compared to the boiling point of the solvent. So what they found that the elevation in the boiling point is depending actually on the number of molecules of the solute in the solution. And it should be noticed here that for each kind of solvent the situation will be different, because the calculation of the change or the elevation in the boiling point, which is the delta TB, equals to KB, that's the constant, the bulloscopic constant, the KB, multiplied by the molality, which is the concentration expression of the of the solute. So for each type of solvent there will be different constant related to the solvent, and for more information about this property, the different equations, the different expressions included in the equation, the students can be referred to pages 229 to 232 in Martin's Physical Pharmacy book. An example on how to calculate the elevation in the boiling point, or the constant for the boiling point elevation, can be showed in this slide. So the calculation for the elevation constant, here the example is saying a 0.2 molar aqueous solution of a drug gave a boiling point elevation of 0.103 degrees centigrade. So calculate the approximate molar elevation constant for a solvent. So using the same equation showed in the previous slide, the molar elevation constant can be easily calculated from the equation. In the previous equation, the elevation in the boiling point delta TB equals to Kb multiplied by the molar concentration of the solution. So in order to calculate the Kb, we have to divide the delta TB over the molar concentration, and by simple substitution of the information mentioned in the example, the constant can be easily calculated, and it will be 0.515 degree kilogram per mole. Now we are going to move to the third property related to the colligative properties of non-electrolyte solutions, and this is the depression of freezing or melting point. Now before going into the details, it's important to define what do we mean by freezing point or melting point. For a pure substance, the freezing point or the melting point can be defined as the temperature at which solid and liquid states are existing in an equilibrium, and this is under 1 atmospheric pressure. Now this is the basic and the simple definition of freezing and melting point. Now for most substances, these substances are existing in different states of matter. So for example, if we are talking about water, it can be existing in vapor, liquid or solid states. So there is a point at which all these states are existing in an equilibrium, and this point or this temperature at which all the phases are existing in equilibrium is termed as a triple point, as you can see in the figure. So it's a temperature at which the three states of matter are existing in an equilibrium state. And this is for water equals to 0.0098 degrees centigrade at 4.58 millimeter of mercury. This is what we call the triple point. So this is slightly different from the ordinary freezing point of water at atmospheric pressure, but the difference is because this triple point is measured at the ordinary vapor pressure of water rather than the normal atmospheric pressure. But anyway, the difference between the two is insignificant, and the abbreviation for the depression in the freezing point is shown in this slide as delta TF. So delta TF, it means the depression in the freezing temperature. Now imagine if we want to prepare a solution, a pharmaceutical solution, any drug, you want to dissolve a drug in any kind of solvent. So what will cause the dissolution process or the process of making the solution regarding the freezing point. So in this case, it is noticed that if you add a solute to a solvent to make a solution, this will cause the escaping tendency or the vapor pressure of the liquid solvent lowered below than that of a pure solid solvent. Okay, so the vapor pressure or the escaping tendency of the liquid solvent is lowered below that of the pure solid solvent. So in order to compensate for the equilibrium state and to bring all these two phases, the liquid and the solid state, to become in an equilibrium situation, the temperature must be dropped to re-establish the equilibrium state, and that's what we call it the depression in the freezing point. And as the concentration of the solution increase, the depression in the freezing point or the melting point become more and more. It should be mentioned here that when a pure solvent is converted to a solid state, it will convert it to the pure solid solvent. So this is solvent converting from the liquid state to the solid state. But if we have a solution, then we do have the solute dispersed in the liquid, in the solvent, in the liquid state. When this converted into the solid state, it will form what we call it a solid solution. So what is solid solution? It's a solution in the solid state where the solute molecules are dispersed uniformly and homogeneously in the solvent. Okay, but this is all in the solid state. So that's the definition of the solid solution. Okay, so that's all about the simple expressions related to the depression of a freezing point for non-electrolyte solutions. Now on this slide, I'm going to show you how to calculate the depression of freezing or melting point for non-electrolyte solutions. The calculations of melting point depression can be easily done using this equation. So the delta F equals to Kf multiplied by thousands multiplied by W2 divided by W1 multiplied by M2. So in this case, the delta Tf is the depression in the freezing temperature, and Kf is the freezing point constant that can be easily taken for each solvent. It's depending on the nature of the solvent. For each solvent, we do have a specific constant that's depending on the nature of the solvent itself. The W2 is the weight of the solute, while the W1 is the weight of the solvent, and the M2 is the molecular weight of the solute. So by using this equation, it's easily and simply very straightforward to calculate the depression in the freezing point. Now, as an example for the calculation of freezing point, now the question is, what is the freezing point of a solution containing 3.42 grams of sucrose and 500 grams of water? The molecular weight of sucrose is 342 grams per mole. In this relatively dilute solution, the Kf is 1.86. So by using the same equation, so the delta F, the equation I already mentioned above, so it can be easily calculate the delta Tf. So the delta Tf equals 1.86 multiplied by thousands, and then this is multiplied by 3.42 divided by the weight of the solvent, and the weight is multiplied by the molecular weight of the solute. So the delta TF is equal to 0.037 degrees centigrade, and the freezing point of the aqueous solution of sucrose is minus 0.037, because we do have the normal freezing point of water is 0, so, and we have depression of 0.037 degrees centigrade, so the temperature, the freezing point in this case of the aqueous solution is minus 0.037 degrees centigrade. Now in this slide I'm going to talk about the fourth and the last colligative property related to the solutions of non-electrolytes. So in this case we do have the osmotic pressure. That's the last colligative property. Before going into the details of the osmotic pressure, I just want to give you some details about or concepts of solutions of non-electrolytes. Now imagine that you have two liquids. The first one is a solution of non-electrolyte, like aqueous solution of sucrose, and the other liquid is just water. Now if you put these two liquids together, the water molecules will move or diffuse from the lower concentration part of the mixture to the higher concentrated, to the more concentrated part of the mixture, which is the aqueous solution of sucrose, and the movement will continue until you reach an equilibrium between the two liquids. So in this case, that's the diffusion state. So we have a diffusion of the solvent molecules from the lower concentration part of the mixture to the higher concentration part of the mixture. Now imagine that we have a semi-permeable membrane separating these two liquids. So in this case also the water molecules try to diffuse from the lower part of the mixture, lower concentration of the mixture, to the higher concentration of the mixture until we reach also the equilibrium. But in this case, because the movement is occurring through a semi-permeable membrane, we are not calling this as a diffusion. It's rather an osmosis process. And the deriving force for this osmotic phenomena is called the osmotic pressure. And the osmotic pressure is a colligative property because it's depending on the concentration of the solute, which is depending on the number of the molecules of the non-electrolyte in the solution. Now, an important question is why this is happening, why the solvent is moving from the lower concentration part of the mixture to the higher concentration part of the mixture. The answer for this is because the chemical potential of the solvent molecules in the solution is lower than that of the solvent, of the pure solvent. And this is caused by the addition of the solute to the solution. So the solute cause lowering in the chemical potential of the solvent molecules in the solution compared to the pure solvent. And that's why the chemical potential in the pure solvent is higher, will cause the movement of the pure solvent molecules from the lower concentration to the higher concentration until the two chemical potentials become equals, become the same, and in this case we will reach the equilibrium status. So that's the explanation why the water molecules move from the lower concentration to the higher concentration parts of the mixture. This is across a semi-permeable membrane. Now, that's just an explanation of what is going on, what is happening, and why the osmotic pressure is depending on the number of particles or number of molecules of the solute inside the solution of non-electrolyte. Now, if we try to calculate the osmotic pressure for a solution of non-electrolyte, we can simply use this equation, which is pi multiplied by V equals to nRT, where pi is the osmotic pressure in atmosphere, V is the volume of the solution in liters, N is the number of moles of the solute, R is the gas constant, and it equals to 0.082 liter atmosphere divided by mole degree, and T is the absolute temperature, so it's not the ordinary temperature, it's the absolute temperature. Now, if we want to give an example for this, example 513 is the calculations of the osmotic pressure of saccharose solution. Now, imagine that we dissolved 1 gram of sucrose. The molecular weight is 342 grams per mole. This gram of sucrose is dissolved in 100 milliliter of water at 25 degrees centigrade. Now, how can you calculate the osmotic pressure of the solution? By using this very simple equation, is easily and simply you can get the osmotic pressure of the solution. So first of all, you need to calculate the number of moles of sucrose by dividing the weight over the molecular weight, and then using the equation you will get the osmotic pressure of the solution, which is in this case 0.71 atmosphere. So that's how to calculate the osmotic pressure of non-electrolyte solutions. Now this slide is showing how to calculate or how to determine the molecular weight of a solute using the 4 colligative properties of non-electrolyte solutions. As we mentioned earlier, that all the colligative properties are depending on the number of molecules of solute inside the solution of non-electrolyte. That's why it is considered as a colligative property. Now, by using the 4 different equations that are used in the determination of the different colligative properties, such as the lowering in vapor pressure, freezing point depression, boiling point elevation, and the osmotic pressure, it's also can be possible to reverse the equation or rearrange it to calculate the molecular weight of the solute in the solution. So these 4 equations are rearranged here in this slide, and by using this equation it is possible to determine the molecular weight of the solute, which is the M2 in this equation, in these equations. So imagine if we have a solution of non-electrolyte and we can measure the different colligative properties and some simple information about the solution, it is possible to identify what kind of solute we have by the calculation of the molecular weight. So these equations are summarized in this slide, and the next slide will show you some examples on how to use these rearranged formulas or equations to calculate the molecular weight of the solute. So at the end of this lecture, I hope that I managed to cover all the topics related to the solutions of non-electrolytes. In this lecture, I covered the part related to the calculation of the different colligative properties, and then the determination of the molecular weight using the same equations with some kind of rearrangement. So in this way we can calculate the molecular weight of the non-electrolyte solute in the solution. And if you have any questions, please don't hesitate to contact me. I'll be very happy to answer your questions, and hope you enjoyed listening to the lectures, and wish you all the best. Thank you for listening.